All right, welcome back, students. Another week of Chemistry of Everyday Life. This week, we are going to discuss Unit 3. So in this unit, we will look at the history and the discovery of the atom, and then talk a little bit about the periodic table and some other properties and what makes up an atom. So this week is the week where we start looking at the fundamental, the basics of chemistry. So it's a little bit chemistry heavy, but this is going to lay the foundation for us for later weeks when we talk more about how chemistry touches every part of your everyday life. Okay, so let's start with some history here. Way back about 2,500 years ago, the predominant thought of the day were in Greek philosophy, right? So around 384 BCE, before Common Era, Greek philosophers mainly, or the most prominent is Aristotle, thought that the entire universe was a single big thing, right? And everything is interconnected, um, and that everything is then composed of four elements like earth, wind, fire, and water, right? And everything is composed of these things, and everything is just continuous, right? Everything is connected. Then comes about 100 years later, at 450 BCE, Democritus comes up with this radical new idea. Instead of everything being continuous, he says that life and everything in it, the matter in life, if you look at it and you go deeper and deeper into it, you can break it down into its tiniest component. And at this tiniest component, it is a solid physical thing and it's indivisible. You can't break it down any further. And he called these things atomos, meaning cannot be divided anymore. Okay? And so this philosophy means that everything in the universe, all the matter, is made up of things called atoms. So here we go. This is Democritus. Seeing him here, very happy and jolly, laughing. But it turns out at this time, philosophy is not quite a science, right? Everything that was known as true comes from just thinking about it. So that's what philosophy is. That's what Aristotle and that gang is all about. And actually all of them, because they at this point didn't come up with a way to test what their thoughts were yet. So because of that, for about 2,000 years, Aristotle and his gangs and their philosophers, their ideas predominated, and the idea of atoms just kind of faded away until in Europe, around 2,000 years later, comes the scientific revolution, where we rediscover this idea of atoms. Okay, so let's forward 2,000 years later. So on this slide and the future slide and a couple of slides later, I'll talk about some experiments and some scientists associated with the experiments that kind of define what that atom, that elusive idea of the atom is. So the first one we're going to talk about is John Dalton. Okay, so there are a couple of observations that John Dalton made. One was that a compound always contained the same proportion of elements by mass. Okay, that means there are that means at this time they already knew about different elements, right? They knew about gold, they knew about copper, they knew about lead, for example, and oxygen and stuff like that. So they knew elements existed, and then they knew there are different types of compounds that is composed of different elements. So what this discovery was saying, that a compound, whatever that compound is, will contain a percentage of an element, no matter how many of it you have. If you have like 1 grams or 1 pound of it or 10 pounds of it, it will always have the same percentage of a certain element. Okay, so that's the first idea. Also, Dalton observed that there could be more than one combination of two elements. So it could be the same two elements, but they can combine together in different proportions, and these different proportions can give you a different substance altogether. Okay, so for example, if you have something that is 2 nitrogen parts to 1 oxygen part, you get a certain compound, a certain substance. Whereas you have a substance that is 1 part nitrogen and 1 part oxygen, right? So equal in their relative mass. So from these two ideas, John Dalton proposed his atomic theory. Okay, so this was his paper published in 1803. And so I'll highlight some of the important parts of his theory. The first is that all matter is composed of extremely small particles called atoms. Okay, so he's hearkening back to this idea proposed by the Greeks 2,000 years earlier about something that is indivisible, right? Something very tiny and small that's indivisible called atomos. So he calls it the atoms. Part two, atoms of a given element are identical in size, mass, and other properties, right? So all these atoms, if they all have the same properties, they belong to a certain element. That's what he's saying. And different elements will have atoms that are different from the atoms of the other elements. Okay. Now, so I highlight this in red because it turns out with later discovery, we find that this concept is mostly true. Okay, but not all the time. Atoms of a given element are identical in mass. It turns out that's not true. Later on, in this lecture, we'll talk about something called isotopes, where atoms of the same element will have different masses. Okay, so there's a tweak in his proposal here, but overall, that seems to be true. Third part here is atoms cannot be subdivided, created, or destroyed. Again, this one is mostly true, but as we discover further that indeed the atom is not the tiniest part, there are smaller parts below the atom called subatomic particles. We'll talk about that in a bit. Atoms cannot be created or destroyed. That's another concept too that we will challenge a little bit when we talk about nuclear chemistry in another unit. But basically, when you have nuclear reactions, you can make new elements, new atoms. The fourth concept here is atoms of different elements can combine in simple whole number ratios to form chemical compounds. This was what we stated in the last slide, where part of Dalton's discovery. And lastly, in chemical reactions, atoms are combined, separated, or rearranged. And so this is very key, right? Atoms, when you have reactions, they don't just make new substance, they just rearrange themselves in different ways to make a new substance, okay? So for example, if you have the element of sodium, which is a metal, and you have the element chlorine, which is a gas, they're very different from each other, right? But when they combine together, they make something called sodium chloride. So 1 part sodium, 1 part chloride. Now, the prior one, the sodium by itself is a metal, and the chlorine by itself is a gas. Both of those are you can't eat. Actually, they're toxic if you consume them. But when they combine together to make sodium chloride, they are table salt, the salt you put in your food. So it's totally edible, right? So they just rearrange themselves in order to make a new substance when they undergo a reaction. Again, this is mostly true to most of chemistry except for nuclear chemistry, which is a very vastly different topic. The atomic theory is the law of the land now. This is what we for sure know is true. So to illustrate this point, researchers from IBM made this movie called A Boy and His Atom, and they made it in 2012. So in this movie, they tell a story of a boy meeting an atom and making friends with his atom, and this atom does various cute things. So the point of this movie, though, is to show that we can actually see atoms. Okay, so it was made by zooming in 100 million times in to see carbon monoxide atoms, and then they move each carbon monoxide molecule. I'm sorry, molecules, not atoms. They move each carbon monoxide molecule and then take a picture of it frame by frame, and then they animated it. So let's go to it and see a clip of it. There you go. All of these are the molecule. So they use a microscope that was super strong that can zoom in and to create this image for us. Yep. So atoms are indeed real, and they will be a guide to us to understand chemistry and therefore predict reactions. A theory is great, but if a theory can help you predict and help you plan or make more experiments, it's useless, right? So this theory is what is the foundation to make all chemistry really possible in the modern day. Okay, so now that we thought about atoms, let's talk about the elements themselves also. So again, we said earlier that elements were already known for hundreds of years prior to this, but because people wanted precious things like gold, so they knew about gold, they knew about mercury, they knew about like copper, like I said. So there were all these elements, and so as scientists, we always try to organize the universe, like how are these elements all related? So many scientists have tried to organize these elements in a way that is easy to see some patterns that come out of it. But Dmitry Mendeleev in 1869 was quite special in the fact that he arranged these elements in order of increasing atomic mass. Okay, and actually other people have done that also. But what his strong point, or his why his organization stood out, is because he noticed that there were some gaps, right? Because as he was organizing these elements out in terms of their mass and also by their properties. So he would arrange them by their properties. So he would see that sometimes that there would be an element that should come next, but yet they don't know it, right? So he left gaps in in his organization. I'll show his organization in a bit. And lo and behold, when these elements were indeed eventually discovered, many of his predictions were true, like their masses or their properties or their reactivity. Okay, so this is an example of his his organization, and it's called the periodic table because the patterns of the element, when you line them up, repeat periodically, repeats every so cycles. That's why it's called the periodic table. All right. So he groups them mainly by their characteristics. You see here, the R just represents the element. In this column here, these elements, if you have two of that, it will form a product that requires two of it to one oxygen, or one of it to one oxygen, or two of it to three oxygen, so on and so forth. So these are these patterns that he noticed. So for example, he lays them out first in their mass. So the first element, and that with the smallest mass is hydrogen here, then followed by lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, right? So all by mass and all by different characteristics. The next element then was sodium. Okay, so this is why it is called the periodic table, because sodium is the next element in terms of mass, but it is very closely related to lithium because it would make the same kind of product with oxygen. So instead of just continuing that way, he basically makes a new row, a new period, hence periodic. And he starts that new row, that new period with sodium. Then he continues again with all the elements by their mass. So sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine. All right, and then again he comes to potassium, and he has to make a new row because potassium reacts a lot more like sodium than anything else. So he indents and then goes to the next row. Then calcium, and then here's the thing: the next element they know existed at a time was titanium. But then he realized, wait a minute, titanium can't be next because it doesn't really act like boron, right? So it acts more like silicon and carbon. So he puts it in this column and leaves this blank, okay? Leaves this next atom blank and predicts that this is indeed going to be an undiscovered, a yet undiscovered atom. and he predicts that it will have a mass of 44. So he does that for a couple of them, right? You see here 44, 68, 72, 100, and so on, okay? Not only does he predict that the mass of these unknown elements, but he also predicts that they will have the same property. That's why they are in the same group. So this element here, he said, will be very much like aluminum. In fact, he calls it beyond aluminum. And then he predicts that this element here is very much like silicon, so he calls it beyond silicon. And indeed, they were discovered as such. So this element at 44 mass unit is called scandium. This element here at 68 is gallium, and both of these behave very much like aluminum, it turns out. And then this element here at 72 is germanium, and indeed it reacts very much like silicon. Okay, so because of this, Mendeleev is known as the father of the periodic table, even though other scientists at the time and previously have also tried to make a periodic table, but his was most useful as in it could predict, you can use it to make predictions, and that later came true. And fast forward to modern day, this is now our current periodic table with so many elements. And there are indeed some elements still yet to be discovered, mostly in the heavier masses one. Yes. So I want to note here, I wrote a note to myself to talk about argon and potassium to kind of make a tweak a little bit, because it turns out the periodic table is not organized by mass. Because when Mendeleev did it, there's a group of elements in purple here that was not yet discovered. It was only discovered up to this column of elements here, but this column was not yet discovered. It's called the noble gases, okay? So when these elements were discovered, it kind of made his plan a little bit not great, right? Because if you organize by mass, then argon, for example, wouldn't go here. Notice that this chlorine is 35.45. Argon is 39.95, okay? Notice that, which is bigger than 39.10, okay? So argon would have followed potassium, but it doesn't, because they notice argon is a gas, first of all, and all of these are like solid metals, like shiny things. So it doesn't make sense to argon to put here. So what happens? So it turns out it's not organized by mass per se, although in general it is by mass. It is organized actually by something called the atomic number. So the number up here, the atomic number, the number on the top, 13, 14, 15, 16, and so on and so forth. That turns out to be the atomic number is the number of protons, concept we'll talk about in just a minute, is the number of protons your atom, hence your element, has. And you can think about the atomic number as like your social security number, right? So everyone has their unique number to identify themselves. Well, atoms or elements have a unique number that identifies itself too. It's called the atomic number. Okay, so before we talk about the periodic table, let me zoom in onto the square here. What is the information you can glean from each square of the periodic table? So the biggest thing here is what is known as a symbol. So the symbol is a shorthand to write the name, the full name. So for example, this is PT, which is for platinum, okay? And there are two numbers on a periodic table. The one number we talked about already called the atomic number, again, which is the number of protons an element has. The other number is called average atomic mass. So the atomic mass is basically the mass of each atom on average. And we'll talk about why is it called on average at the end of this lecture. Okay, so we'll come back to that. All right, so now let's take a look at this periodic table again, looking at some features, the way it's organized into what we call as groups or families. All right, so each column is called a group. So this is group 1, group 2, group 3, so on and so forth. And it turns out there's two systems for this. The first system, as you see here, from 1 all the way to 18. The second system just ignores this chunk in the middle and calls this the transition metal. And we call the group 1 and group 2 13 to 18 as the main group elements. So in the main group element, then you can just rename it as 1, 2, ignore 3, 4, 5, 6, 7, 8. Okay, so if you see it written two different ways, that's the reason. So this could be group 18 or group 8, but in the main group. Okay. And then there are some, that's the column. Now the rows are known as periods. And in the previous slides, I talked about why it's called a period, because of the pattern and the recurring pattern. So every time it repeats itself, that's another period. So you go down to the next row, basically. Now, zooming back, looking at this whole periodic table, let's look at let's look at one feature called the metal characteristics. Okay, so you can describe elements in terms of being a metal or not, a non-metal. And then there's something called the one in between called the metalloids. Okay, so basically, let's talk about the non-metals because there's less of them. So anything in pink over here in group 8, and the turquoise here in group 7, and then the red elements here. So those three categories are called non-metals. And then you have these gray elements in the middle called metalloid, and everything left of that, so everything else, is called metal. Okay, so they are divided in that way because of the characteristics that they have. For example, all the metals, right? Not all, but basically all but one maybe, are solids. Do you know which one is not a solid in the metal? Mercury. Mercury is actually a liquid. But nonetheless, everything else is a solid and is shiny and is hard and can conduct electricity, for example, right? So they all have the same characteristic on the left-hand side. Okay, minus hydrogen too, because hydrogen is not a metal. It's over here because it sometimes acts like a metal, but sometimes acts like a non-metal. Okay, exception. All right, and then on the right-hand side, we have the non-metals. Non-metals, opposite of the metals, right? So they're not solid all the time. Some of them are solid, but some of them are gases, and some of them are liquids, okay? So for example, oxygen, right? That's a gas. And then bromine, that's a liquid at room temperature. They aren't very shiny in particular. They're actually dull if they are a solid. If they're gas, they're invisible, right? And they don't conduct electricity very well, for example. And so you have the metalloids in the middle. As you can see, if they're in the middle, they share characteristics of both groups. So they share some metal characteristics and some non-metal characteristics. Okay, so these are the metalloids. The most popular one is, for modern age, silicon. But yeah, that's a kind of a wide view of the periodic table. Now let's kind of zoom in a little bit. As we talked about earlier, that each column is known as a group or families, because all of the elements in this column will have very similar characteristics, similar reactivity. Okay, so the first group, and you should know these by names, because I'm going to go over only a few of them by name, so you should know the ones I go over. Okay, so the first group is called the alkali metals. Okay, so they include hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. Notice that as we go down the periodic table, the names seem a little bit more obscure, a little bit, you will know them less, right? They're less prevalent in nature. The ones on the top is what we would hear on a day-to-day basis, maybe. We know them more. Okay, so like the name suggests, they are metals. So they are shiny. They are hard. It conducts electricity, like I said earlier. Minus hydrogen. Remember, I said hydrogen is not a metal, but sometimes it acts like a metal in some way. So that's why it's put in this column. Okay, so one prominent example of this is the lithium in your lithium battery, which is like a super big deal now because that's the driving force, one of the driving force behind our electric vehicles, right? It's the ability to make these lithium batteries. And then next is sodium, our most easily recognized example is the sodium in sodium chloride, which is your table salt. Now notice that we said it was metals or shiny and whatnot, right? But table salt is not, right? Because it's sodium chloride. It just has sodium in it. Once sodium combines with chlorine to become chloride, it changes its chemical properties and whatnot. That's why it doesn't look like what we think of as metal. But I don't just want to show metals because all of them will look the same. You know, they're all just blocks of rocks that are shiny. So for example, this thing, right? Yeah, so I didn't want to show all of them looking like just this. But here's our next group. Group 2 is known as the alkaline earth metals. They include beryllium, magnesium, calcium, strontium, barium, and radium. So the picture I've shown here is magnesium, but I could have fooled you and said it's any one of them because they, again, look very similar to each other. But the form that maybe you know them more is the fact that magnesium, you can get you need it in your diet, right? But the best source for them are in these leafy green veggies. Calcium also I can show you as just shiny metal, but the form that you might recognize them is in your dairy products, right? So calcium in your dairy products. So next, the next group that you should know are the halogens. So the halogens, by the Greek name, means to make salt, right? Because the elements in this group, when combined with sodium, for example, will make what is known in chemistry as salt. Our most prime example is table salt. So when chlorine, for example, combines with sodium, it makes sodium chloride, which is this salt here. Another salt is the fluoride that's in your toothpaste, right? But so there's no real pictures to show fluorine and chlorine because they're gases. But when they're combined with other things, they are solids, as you can see here. Okay, but this is group 7, including fluorine, chlorine, bromine, iodine, acetine, and tennessine. Okay, again, the ones on the top are a little bit more well-known than the ones on the bottom. Iodine is if you've taken like a given blood, or you had to have an like a line, an IV line come out, they usually sanitize that area with something that's a little bit brownish in color. Yeah, that's to kill the bacteria and stuff. And that's basically iodine solution. So you've seen that maybe. Okay, so that's called the halogens. The last group I want to point out is group 8, known as noble gases. And again, these were discovered much later than the other groups because they didn't react much. They didn't react much with anything else. That's why they call them noble. You know, they just keep to themselves. They don't really interact with the other elements. And they're all gases, okay? So they exist in the form of gas. So we have here helium, neon, argon, krypton, xenon, right? So those are probably radon, the ones we know. And this one, I'm not even sure how to say. Organoson? I don't know. Again, things on the top are more familiar to us. Okay, so helium, you all know, right? Balloons, helium balloons is what you fill it with that gas to make it, it's lighter than air, so therefore it floats into the sky. Another gas filled in a tube and then run electric current through it gives us lights, give us neon lights, right? So these are tubes filled with neon gas, basically. And then argon, you might know argon or may not, but if you drink wine, you have to thank argon for keeping it in good shape, right? So they pump argon as a gas on top of the wine barrel, so replaces all the oxygen and the other air out. Because the oxygen will, if you leave oxygen in with the wine, over time it will react with the alcohol and make acetic acid. So instead of drinking wine, you're going to drink vinegar, for example. So if you have argon in there, argon is noble gas. It doesn't react much with anything, so it's just going to keep things unreacted. So it's going to preserve your wine basically. So those are the the families of elements you should know and be familiar with. All right, so that's the elements, that's the atom. Now let's transition to look to ask, what is the atom? What is it made up of? Okay, so we're going to go below the surface to go into the components of the atom. We're going to take a look at the subatomic particles. And I'm going to talk about a couple of experiments that was instrumental in discovering these different particles. Okay, so the first one is called the Thomson experiment. And so what the Thomson experiment is you shoot a ray of light through this evacuated glass tube here. So it should go straight, right? And then you can apply some kind of electric field or magnetic field, and somehow that electric or magnetic field can bend this light. Okay, so in 1897, J.J. Thomson, the scientist, discovered this effect and therefore discovers this part of the atom called the electron. Okay, again, it shows that he can bend this the cathode rays, meaning that these rays consist of a charged particle. And so these charged particles are also discovered as negatively charged. So these electrons they discovered are negatively charged. So that's the first component of the atom, right? So Thomson and the scientists community at the time proposed a model for this for the atom, and in this model, it's called a plum pudding model. Sometimes it's like a muffin. That's what a plum pudding is. And basically, they imagine an atom where electrons are just sprinkled throughout, and the mass of the atom is just also evenly distributed. Then comes Rutherford, who makes this gold foil experiment. So he has a gold foil, so foil full of gold atoms. Then he kind of shoots these beta particles or these tiny particles at this gold metal. And in the Thomson model, if everything is evenly distributed out like that, then when you shoot these particles at the gold foil, it should just go through straight through. But what he discovered is that when he shoots it, most of it does go through, but some of it ricochets back, like shoots back in the opposite direction or at an angle. So this discovery in 1911, Rutherford discovers that there must be a very dense inner core of an atom, and he calls that the nucleus. And he shows that the mass of the atom is actually at the central core. Okay, and therefore these particles in the nucleus are then discovered to be protons, and protons are then also discovered to be positively charged, so they're opposite of the electrons. So these particles are inside the nucleus, whereas the electrons are outside of the nucleus. These protons are positive, the electrons are negative. These protons have mass, the electrons, by comparison, do not have mass. So these protons also turns out to be the one that dictate the characteristics of the atom, right? So every element will have a characteristic number of protons. If you have 6 protons, you are element X. If you are 7 protons, you are element Y. So every element will have a unique number of protons. This number of proton is also called the atomic number. They're so important. They define the element so much, they call it the atomic number. That's the Social Security analogy I used earlier. All right, so there's this one last piece of the puzzle, okay? And this one was discovered by another scientist, James Chadwick. He discovered the neutron. And these particles turn out to be also in the nucleus, and they also have mass, but unlike the protons, they're neutral. They don't have a charge, zero charge. So here's our big picture of the atom. So on the outside, we have electrons, very tiny, no mass really compared to what's inside the nucleus, which are the protons and the neutrons. They both have mass and they're equal in mass. Protons are positive, neutrons are neutral. Okay, so let's summarize all of that information. Proton with a symbol of P, like I said, have a positive 1 charge. they live inside the nucleus and has a mass of a unit called atomic mass unit, AMU, of 1, same as the neutron, except the neutron doesn't have a charge. Opposite of that, the electrons is negatively charged and has such a small mass that we say it's basically 0. So the mass of the atom comes from what? You just have to add up the number of protons and the number of neutrons, right? So you have if you have 1 proton and 1 neutron, your mass is 2 AMUs, right? So that's where the mass number comes from. So every atom will have a mass number, which is basically its mass. Okay. Note that it's not the average atomic mass. So keep that in mind. We'll come back to this idea later. It's not the atomic mass. Mass number is a little bit different, even though you might easily confuse them. Okay, the mass number is the mass of an atom, and we'll explore a little bit further this concept. So for example, the common hydrogen, okay, I'm saying common for a reason here because there are other types of hydrogen. The common hydrogen atom in this table, you see here, it has 1 proton and 0 neutrons. So what is its atomic mass? 1 plus 0 is 1, right? So its atomic mass is 1. Whereas helium, atomic number 2, because it has 2 protons. It turns out the common helium has 2 neutrons. Awesome. So what is its atomic mass? 2 plus 2 is 4. Very good. Now let's go the opposite way. Let's say you are lithium, this type of lithium, which means you have 3 protons, but you have 7 is your mass number. So how would you get to this number? Remember, these 2 numbers add up to be the mass number, right? So you can do reverse. So 7 minus 3 will give you 4. So if that information was like blocked out, you can say, okay, 7 minus 3 will give you 4, so you have 4 neutrons. Let's do an example. We have here our friend chromium. Certain atoms of chromium have mass number of 52. How many subatomic particles does it have? Okay, so give me all of the subatomic particles and how many are there? So let's first, the easiest one you should be able to decide is protons, right? How many protons do you think chromium has? Its atomic number, right, on top there is 24, so it has 24 protons. Next easiest number to determine is electrons. In an atom, electrons and protons are equal because the atom will be neutrally charged. That means it's 0 charge. So if you have 24 positive, you also need 24 negative, right? So that's why you have 24 electrons. Okay, and the last one is the hardest one is the number of neutrons a certain atom of chromium has. And how do we figure it out? Based on our previous example, you take the mass number minus the number of protons, it will give you number of neutrons, right? So 52 minus 24 is equal to 28. So it has 28 neutrons. So I've been saying things like a certain type of chromium, right? So it turns out there are different types of chromium. And what makes them different is the number of neutrons it has. They all have the same number of protons, right? Because the number of protons dictate your identity. But they have, but different chromiums may have different number of neutrons. And if they have different number of neutrons, they will also have different mass number. Logically makes sense, right? Okay, and so these are called isotopes, by the way. If you have, if you're all the same element, but you have different mass, you're called different isotopes. And basically all elements will have at least 2 isotopes. It's just a matter of percentage of the existence of the different isotopes. Sometimes it's like a 50-50. Sometimes it could be like 99% and 1% of one isotope versus another isotope. All right, so if we were to talk about this particular isotope, we can write it in this fashion here with a symbol CR, elemental symbol CR. And on the top left hand, we will write its mass number, 52. On the lower left hand is its atomic number. Now notice the atomic number and the elemental symbol is quite redundant, right? Because if you know you have 24 as your atomic number, you know it's chromium. So why even bother writing it? So because of that, we can get rid of that number and write it this way with an elemental symbol, with a dash, and then the mass number. So this will tell us exactly that this is the isotope of chromium with 52 as its mass number. Therefore, 28 neutrons and 24 protons. Okay, so let's take a look a little bit further about this idea of isotopes. Right, so let's take a look at hydrogen, for example. So hydrogen, as you can see here, this particular isotope is the most common form, the most common isotope. That's why we're just going to call it hydrogen. It has a mass number of 1. What does that tell you? It must, all hydrogens have atomic number 1, so it has 1 proton, right? But if its mass number is 1, how many neutrons does it have? 1 minus 1 is 0, right? So it has 0 neutrons. So hydrogen will have 0 neutrons. What about deuterium, which also has 1 proton? So it is also considered a hydrogen, an isotope of hydrogen, but its mass number is 2, which tells you it has 1 neutron, right? Let's do it again. Tritium, also atomic number 1. So it's also considered an isotope of hydrogen, but its mass number is 3 because it has 2 neutrons. Very good. 2 plus 1 is 3. Okay. Now, brings us to the next concept of atomic mass. This is the number written below here. Okay. Notice that this 1.008 is not any of these numbers. It's not 1, it's not 2, it's not 3. This is the average. If you take hydrogen as a whole, what is the average weight of hydrogens? And because hydrogens have different weights, different masses here, we can take a weighted average, meaning this hydrogen, H1, is the most abundant, so it would contribute to the most mass, whereas H2 and H3 is more massive, it's heavier, right? But it doesn't exist that much. So if you average all of these out by the percentage of their existence in nature, you will come out to be 1.008 AMU. Okay, so there you go. That's the atomic mass. That's the difference between atomic mass versus mass number. Okay. So quiz question then. Is there any hydrogen atom that weighs exactly 1.008? The answer is no, right? Because that's just the average of them. That's like saying, for example, there's only 2 humans on this one planet, okay? And one human turns out to be a baby, and let's say that baby weighs 10 pounds, and the other human was an adult that weighs 100 pounds. And then this alien would say, what's the average weight of a human, right? What would you say? What's 10 plus 100 divided by 2? So the average weight of a human is 55 in that case, right? But there's no one human in this universe that you can't find a human that weighs 55 pounds. Because one weighs 10 and one weighs 100. But that's what the average would mean in this case. That's a very simple scenario to kind of explain what that is, explain what the atomic mass is. Let's do another example. Let's say now there's 3 humans. One is 10 pound, one is 100 pound, another one is 100 pound. So the 100 pound exists more than the 10 pound, right? So what's the new weighted average? Would you guess to be 55 or higher or lower? Let's do it. 10 plus 100 plus 100. Since there's 3 now, we have to divide it by 3. It's 70, right? So the weighted average has shifted because there's more people that weigh 100 pounds than 10 pounds. That's why the more abundant a sample is, the more the average will be closer to that sample, right? So if there were 99 people that weigh 100 pounds and only one baby that weighs 10 pounds, then the average would be closer to 100. Okay, so that's how atomic mass works. Okay, and then we're going to end this lecture today talking about one particular isotope that is of quite important interest, and we'll talk a little bit about this one even further when we talk about nuclear chemistry later on in a later unit. So let's talk about the atomic bomb, and the element of interest here is uranium. Okay, and the isotope of interest to be particular because there are two types of uranium. One called U-238, the other called U-235. But only one of these is important in the atomic bomb. It turns out U-235 is the reactive form of the isotope that can make an atomic bomb. However, it's only 0.7% found in nature. The other times you see it, it is the other isotope, right? You need then to collect a sample that has much more U-235 than you would find in nature. And that process is called enrichment. So that's why sometimes you hear the word enriched uranium. You need enriched uranium, for example, to even do for nuclear power plant. But in terms of being a weapon, it needs to be not 0.7%, but 90% of U-235 in order to be good enough to use as an atomic weapon. Okay, so that's what one application of the isotopes we can see in our in the news in our everyday life. The word enrichment. Yeah, this does round out our lecture for this unit. As a recap, we started talking about the history and the discovery of the atom. Then we talked about how the atom represents an element and how that's organized into what is known as periodic tables and their families and whatnot. Then we end our lecture today with taking a look at what is the atom itself, what makes up the atom, and the subatomic particles. All right, so in the future or in the next lecture, we'll dive more into these elements and won't focus really much on the protons and neutrons anymore, but focus on the electrons because that's the key thing that will drive reactivity of most of chemistry, basically all of chemistry besides nuclear chemistry.